Alright, gang, here we go. Chem 2, Unit 7. We're talking about real gases. Alright, I love these kind of lectures. This is when we get to peel back the curtain a little bit and take a gander at those times where we've had sneezing trees in our understanding so far. So this is one of those times where we get to really look at, well, we've made a lot of assumptions. I wonder what the real world looks like. Alright, so if you remember, the last couple of videos we talked about the kinetic molecular theory and ideal gas equation, right? That's primarily what we've been focusing on the last couple of videos, and we made some very important assumptions about both of those things. Specifically, in kinetic molecular theory, there was a series of 5 assumptions that we made, okay? And there's 2 of those that fall drastically apart under certain conditions, okay? And that's kind of where we're headed at first. So this first bullet here says, in the real world, the behavior of gases conforms to the ideal gas equation only at relatively high temperature and low pressure. Okay, now what do they mean by that? Well, high temperature, this is stuff around about 300 Kelvin. Okay, and low pressure is about like somewhere around 1 atmosphere. All right, and if you're a clever chem student, you recognize, well, 300 Kelvin is awfully close to like about where we are at room temperature. Room temperature is defined at roughly 25 degrees Celsius, and that's at like 298 Kelvin. Okay, and then 1 atmosphere happens to be about room pressure. Okay, so in the laboratory conditions, under standard laboratory conditions, we do our experiments at high temperature and low pressure. Okay, defined by the ideal gas law. And so that's why we use ideal gas equation so much in chemistry, is because it does a really good job of predicting gas behavior for 99% of laboratory conditions. All right. However, if we start varying from these things, gases will show wildly different behavior even under even the same gas as we go to high temperature and different pressures. All right. So for example, in this little graph here, notice that up to about 1 pressure, okay, so this is zoom in on this box. The y-axis on these is PV over RT, okay, or N, the moles, okay, and then the x-axis here is in pressure, atmospheres. Okay, now if the ideal gas equation was perfect, this would be a 1-to-1 relationship. Okay, and so you'd get a perfectly horizontal line all the way across. But notice that here our noble gas, okay, follows, or our gases here follow the ideal gas equation up until a certain point. All right, and then after that they start to vary. Okay, and so after that point, look what starts to happen as we go up. Hydrogen just kind of completely just goes up at a nice line, linear straight line there, but the other molecules aren't so nice. Like carbon dioxide, look at this weird shape he does. He veers drastically downward until about 100 atmospheres, and then he starts to shoot up at a pretty steep angle there. Okay, slope. And then nitrogen here, look at him, he goes down a little bit and then comes back up as temperature keeps, or pressure keeps going up, and then same thing with methane. All right, and so you can see that these gases will change their behavior. And so really it's like, well, what's causing this? Why doesn't the ideal gas equation hold true? All right, so really what we need to do is we need to look at, well, what were some of the assumptions we made in the ideal gas equation that might not be benefiting us? Okay, so the first idea was that one of the ideas is that we made the assumption, okay, that gas molecules had negligible volume. Okay, all right, so the gas molecules have negligible volume, all right, and that there were no attractive forces between the gas molecules. These tend to break down at high pressure and low temperature. Okay, so think about it this way. In this container, we've got low pressure. Here's our molecules. Look how much empty space there is. If you took up all the empty space and added up and then compared it to all the empty space taken up by, or all the space taken up by the individual molecules, the percentage of the volume that the molecules took up would be drastically lower in this left piston than it is on the right piston. There's a lot more volume as a fraction or a percentage being taken up in the high pressure situation. So as you start to get to higher and higher pressures, the volume of your molecules becomes much more important, because those volumes are the molecules is starting to take up the volume of the space that your molecules can move around in. And since molecules can't move through each other, okay, it starts to become really important. And so as those molecules start hitting start taking up that space, okay, it lowers the available volume, so it increases the pressure because there's a whole lot more collisions. Okay, so whenever you get to high pressure, right, you start to have to worry about the volume factor of these gas molecules. You have to start keeping track of, well, how much volume do these gas molecules actually take up in regards to the volume of my container. All right, and then on the right, we're talking about intermolecular forces. How do these molecules affect one another? Okay, so here's a gas molecule here, and it's bouncing around. It'll bounce off the walls. And under ideal gas equation with a kinetic molecular theory, we just assumed that every single collision between these molecules was completely elastic. No momentum was lost, right? They kind of hit it like just a bunch of ping pong balls, right? They'd hit each other and bounce off and hit each other and bounce off and hit each other and keep going, right? But as temperature goes down, okay, these intermolecular forces have more and more time and have more of an effect on the motion of these particles. Okay, and that's partly because, imagine it this way, like intermolecular forces a lot of times act like magnets, right? It's just a positive and negative, that are dipole-dipole interactions, these two magnets pushing on each other, okay? And so we know, like, imagine you're holding two magnets in your hand, you got one in one hand, one in the other, and you go like this really fast across your hands. The magnets will attract each other, but because they're going by very, very fast, they don't really pull your hands together very well, right? So you go, and they don't really do much. However, if you go by really, really slowly, like this, you definitely feel that attraction of the magnets pulling your hands together. Okay, same idea here, right? When we are at a lower temperature, the molecules are going to be moving slower. They have lower kinetic energy. Okay, so they're going to be moving slower, and because they're moving slower, they're going to stick close to each other longer. Okay, and because they're sticking close to each other longer, these molecules will be attracted to each other with more effect. Okay, all right, more efficacy. Okay, so anyway, so at high temperatures, that doesn't really matter, right? Because these molecules are moving so fast, they can blow right past each other, and intermolecular forces don't really do nothing. At low temperatures, they're moving a lot slower. Okay, so these intermolecular forces start to matter. Okay, so to recap, at high pressures, we have to watch out because the volume of our container, okay, starts to be taken up by the volume of the molecules at a higher percentage or higher rate. At low temperatures, we have to start worrying about the intermolecular forces. Okay, so in order to correct for these two things, there are lots of different adjustments that people have made to the ideal gas equation to try to take into account these things. All right, probably the most common one, all right, is this one here called the van der Waals or the van der Waals equation. This guy right here. Okay, and it's got two important adjustments. All right, it uses a pressure adjustment. Okay, to account for the fact that these molecules attract and repel each other. And then it also has a volume adjustment that accounts for the fact that these molecules take up their own space. Okay, have some space on their own. So this is the van der Waals equation. I'm pretty sure it's the most commonly used one because it's kind of the easiest to use, and it also looks very similar to the ideal gas equation. All right, so here it is in all its wonder. This is the van der Waals equation right here. Notice that we essentially have just our pressure, our volume is equal to nRT. PV equals nRT. Okay, and so here's our pressure component, and notice that we've got this new factor in here. And this factor here, so this is our moles squared times our A. Now the A is this new factor here, okay, that helps us keep track of the intermolecular forces. Okay, the intermolecular forces, this attraction that they feel towards one another. Okay, so it's in liters squared times atmospheres over moles, okay, squared. All right, and then that's over volume squared. Okay, and so essentially what this does is it helps us keep track of this factor. Okay, how much is our pressure being raised because of this attractive force? All right, and then our volume here, okay, the volume component subtracts out the moles and this B constant. Okay, this new B constant is this guy here. It's in liters per mole. Okay, so it is essentially, once you multiply by liter or moles, it's just in liters. Okay, and it helps us keep track of the amount of space or the amount of available volume that's being taken up by our atoms. Okay, so anyway, so at any given a molecule on this table, all we have to do is to apply the van der Waals equation is just solve for whatever variable we want, okay, and then plug in our variables. And in order to do a PV equals nRT problem anyway, okay, you'd have to have PV and RT anyway, and now we have A and B. So there's nothing new. You just have to have access to these variables, okay? So I wanted to walk through a couple of problems real quick. I really like this problem they do because it kind of gives you an idea of what to do in these kind of problems, okay? So it says if 10 moles of an ideal gas were confined to 22.41 liters at 0 degrees Celsius, it would exert a pressure of 10 atmospheres. Use the van der Waals equation in table 10.3 to estimate the pressure exerted by 1 mole of chlorine at 22.41 liters at 0 degrees Celsius, okay? So essentially what we need to do, okay, is find the pressure, okay, of this chlorine gas, but we're going to use the van der Waals equation to get there. Okay, so that's what they've done here. So they're going to rearrange this van der Waals equation. So let's do that real quick. We'll do that right here. All right, so if we're going to rearrange the van der Waals equation, we'd have to divide by V minus NB real quick. So we'd have pressure plus N squared A over V squared is equal to nRT over V minus NB. All right, and then we'd subtract over the N squared A over V squared. So pressure is equal to nRT over V minus NB minus N squared A over V squared. All right, so that's that. That's our formula there. Okay, and this is exactly what they do. So they're going to rearrange it to isolate P, and then here's all their values. Okay, their N is 10. All right, R value is 0.0821 because we're in atmospheres. Temperature, volume, A value, B value for chlorine. All right, and then they simply plug all these guys in. Come on, do it, do it. There it is. Okay, so here's our pressure. All right, so this was that first part. Okay, and then there's the second part plugged in. All right, so notice this is the 10.26 minus 1.29. So this would be the pressure of chlorine gas. Notice it's significantly lower, okay, than the original 10 that we thought we should get. Okay, so let's look at this comment and analyze exactly what they're saying. It says, notice that the term 10.26 is the pressure corrected for the molecular volume. All right, so that's the pressure collected for the molecular volume. Notice that this is higher than the ideal value of 10. And that's because this volume that was taken up is taken up by those molecules. So they have actually a smaller container than what we assumed in our ideal. So because it's a smaller container, their collisions will increase, so the pressure should go up. And that makes sense, which is what we got. Okay. So they said, thus the molecules collide more frequently with the container walls, and the pressure is higher than that of a real gas. All right, and then they say the term 1.29 atmospheres makes a correction in the opposite direction for intermolecular forces. All right, so it makes sense. Like this should lower the pressure because those intermolecular forces, they'll be attracting one another, so they'll be going slower in general than what we are planning. Okay, so they'll hit the outside containers less often. Okay, and because this correction for the intermolecular forces is the larger of the two, the pressure is 8.97, which is smaller than what would have been observed for an ideal gas. All right, so you kind of get an idea of it's really just kind of a balancing act, depending on the A and the B values. All right, sometimes depending on some temperature and pressure conditions, you know, the intermolecular forces will be more important for its deviation from the ideal gas, and sometimes the volume it takes up will be the more determining force. And really, the only way to figure it out is just by doing the van der Waals equation. All right. Okay, so let's do one on our own, and then we'll call it a day. All right. It says calculate the pressure of a 2.97 mole sample of N2 in a 0.75 liter flask at 300 degrees Celsius. So I'm just going to go ahead and change that. So that should be 573 Kelvin. Okay, using the van der Waals equation, and then repeat the calculation using the ideal gas equation within the limits of the sig figs justified by these parameters. Will the ideal gas equation overestimate or underestimate the pressure, and if so, by how much? All right, so first step, using the van der Waals equation, figure out the pressure. All right, so we got to figure out the pressure using the van der Waals equation. So we already derived this once. I should have wrote it down on another piece of paper so I didn't have to go backwards so much. But that's kind of what we're going to have to do, isn't it? nRT, all right, so nRT over V minus NB. minus NB. I'm kind of doing it backwards because I didn't think this through. Minus N squared A over V squared. N squared A over V squared. All right, so there it is. Right, and I just looked at the variables here in order to figure out what was going on. All right, now we can start plugging in our guys. Okay, so our pressure, our moles was 2.975. Okay, and then the R value, well, we'll just do atmospheres, 0.0821. And then the temperature was 573 Kelvin. All right, and then we're going to divide by our volume. Our volume is 0.75 minus our moles, 2.975, times our B value. Shoot, now we got to go back and look. So we're in N2, so we got to go all the way back here. So N2, our B value is 0.0391. All right, 0.0391. Okay, now we're going to subtract out our N squared, so that's our 2.975 squared, times our A value. All right, I don't know why I have to click it so much, into 1.39. All right, 1.39 over V squared. So that's just 0.75 squared. Nailed it. All right, so pressure equals, and when I do these, I always like to do it in the chunks here. So we'll do 2.975 times 0.0821 times 573 divided by parentheses 0.75 minus parentheses 2.975 times 0.0391. All right, so on the left, I got 220. I forget something. No. All right, 220.9 atmospheres. All right, that's from this part of it. And then on the right-hand side, I have 2.975 squared times 1.39 divided by 0.75 squared. All right, 21.87. 87 atmospheres. All right, and then we can subtract those. So 220.9 minus 21.87, and then I get 199.0 atmospheres. All right, so that's what van der Waals equation says should be the pressure at those conditions. All right. All right, notice it's a very, very high temperature, and it's pretty strong pressure. It's pretty high. It's pretty high. Anyway, all right, and then it wants us to do it as well with the ideal gas equation and compare them. Well, this is easy compared to that, because PV equals nRT, so that means it's just nRT over V. Okay, so our moles was the 2.975 times our R value, 0.0821, times our temperature, which is 573, times our volume, or divided by our volume, 0.75. So we'll take 2.975 times 0.0821 times 573 divided by 0.75, get 186.7. 86.7 atmospheres. So notice that our the ideal gas equation will underestimate what it should be by about, what, 12.2, 12.3 atmospheres. Okay, so in this case, before it was the opposite way, right? It overestimated. In this case, it underestimated. So it all just depends on where you are on your curve, what gas you're looking at, and its factors as far as its intermolecular forces, how much it affects one another, how much volume it takes up, etc. So this was it for our Unit 7. Congratulations, you made it to the end of the 7th unit. First unit back from the semester break. I'm so proud of you. Just keep on keeping on. Do your homework problems. Let me know if you have any questions, and I'll see you on the flip side.